You can see. Okay, so Paul is giving a talk on the statistic of kmers from a sequence undergoing a simple mutation process without spurious matches. Thanks, Paul, for the talk, for giving this talk, and please, you can start.
All right, thanks. So this is joint work with Antonio Blanca, Robert Harris, and David Koslicki. We're all at Penn State University, and this is a paper that this is based on a paper that will appear in Recom, but is already available in bioRxiv. So in this talk, I'll first introduce the model, then give a few motivating applications, and then look at the distribution of the number of mutated kmers in this model, and conclude by providing a confidence interval based on this. We'll then apply this technique to other random variables and give some experimental results. So here's a simple generative model of a genome, of a pair of genomes. We start with a genome A. We mutate every nucleotide with some probability R1. So here there are 3 mutations that happen, and we get a new genome B. The one assumption we make in this model is that all the kmers are unique, both in A and in the new B. And this assumption we'll see later on, but in general it tends to be valid when the K is large enough. Now in this model we are not observing the nucleotide sequences themselves, but we're observing kmers. And anytime we're working with de Bruijn graphs or other kmer-based methods, this is often what's happening. Here I have a convenient way to show all the kmers that are in this genome with each kmer being a dot or circle indicating the kmer starting at that position. So here I'm going to take k equals 3, and so I have every single kmer, like this is the last kmer of the genome, and I'm going to observe that each of the nucleotide mutations also affected k other kmers. So those kmers also became mutated in this case, and in this case these 2 nucleotide mutations together jointly affected these 5 kmers. We can, for example, then observe the number of mutated kmers. So in this case that would be 8, and that would be a random variable whose distribution is given by this generative model. But we might observe other things. For example, we might observe the Jacquard similarity between the kmers of A and the kmers of B. If you recall, this is just the number of shared kmers divided by the number of total kmers. And in this model, where the number of kmers in both sequences stay the same because we don't have any indels, and the only way to create non-shared kmers is through mutations. In this model, the Jacquard can be written as L, which is the number of kmers, minus the number of mutated kmers, over L plus number of mutated kmers. We might also observe the Minhash Card. So in this approach, instead of looking at the full kmer sets of A and B, we first create a Minhash sketch of A and a Minhash sketch of B, and we compute the Jacquard between those Minhash sketches. We call that J hat, and classical results tell us that it's a good estimate of the true Jacquard. So these are just some of the variables that you might observe in this from the simple model. Let me give a couple of motivating applications. The first is the match distance. This is a great paper from Ondoff and colleagues in 2016, and it was actually part of Carol's talk already. So here we start with 2 evolutionary related sequences. We observe this J hat, this Minhash Jakarta estimator, from the 2 genomes. And now we assume that the genomes evolved under the simple model which I just presented, and based on that get an estimate of R1 from J hat. And a point estimate is of course really great and useful, but wouldn't it be nicer to have a confidence interval instead? And what that means here is that you're given these 2 sequences that evolved under the simple model, and you've observed some number of mutations. What is an interval that will contain R1 with 95% probability. Now, for example, R1 could be between 0.4 and, or say 0.1 and 0.2 with 95% probability. Here's another application, and this is in several papers in one form or another, where we have alignment of reads to a reference, and the reference is the Brown graph, which means that we're not looking at nucleotide matches, we're looking at kmer-based matches. In this model, we have that a read is generated from some genome location, and again, we can take this simple model as an approximation of the sequencing error rate that's introduced. But here the R1 is this sequencing error rate, which usually we know, at least approximately. It's not like in the previous case, the biological mutation, which we don't know. So here then the question becomes different. An aligner wants to either accept or reject the putative genome location as a possible alignment. Okay? And what it does at that location is look at how many kmers don't match, and that becomes n-mute. Well, yeah, so in this case 8. And we want to accept or reject this alignment with 95% chance of being correct. And in statistical terminology, what we want here is a hypothesis test with significance level 95% for n-mute. In other words, given R1, so we know R1, what is the range into which the observed number of mutations would fall with 95% probability? So it could be if R1 is 3%, then n-mute should lie between 5 and 7 with 95% probability. And in that case, you would reject this alignment. Of course, 95% is just a placeholder. In theory, we're going to use some general alpha in here. So now let's look at the distribution of the number of mutated kmers, because this is the starting point for any kind of statistical analysis. The expectation of n-mute is easy, and it's done in a lot of papers. This is not new. But let me do it a little formally here. Each of these kmers we can represent with an indicator random variable xi. That would be the kmer starting at position I, like here would be x6. And it's 1 if that kmer is mutated, and it's 0 if that kmer is not mutated. The expected value of each xi is then just the probability that a kmer is mutated. And this is 1 minus the probability that it is not mutated, which is the probability that each of the k positions is not mutated. So we have this expression, which we'll use rk as a shorthand for. Now the number of mutated kmers is just then the sum of these xi's, and if we want the expectation, then by linearity we can move that expectation inside the sum, and we get that it's L times rk. Okay, but let's, and this is where every paper that I'm aware of kind of stops, and here we wanted to go further to understand the distribution. The first thought maybe you have is n-mute a binomial? A binomial is a sum of independent Bernoulli trials, and n-mute is indeed a sum of Bernoulli trials, but these trials are not independent. And the way you can see that is that nearby xi's are dependent. If my neighbor if my xi plus 1 is mutated, that increases the chance that I'm mutated. And this is because the kmer mutation occur in these clusters. But observe though that far away, the xi's will be independent. Okay. So let's capture this dependence with a lemma in the form of the joint. We want to write down the joint probability distribution of xi and xj. Now, if they're far away, then those variables are independent. So the joint is just the sum of the individual probabilities. But if they're nearby, then the joint distribution is given by this formula. And this is not a difficult proof. The way you would do it, here we would visualize the xj as an orange box and xi as a blue box. and you'd break your analysis down into 3 cases. In the first case, you would have at least one mutation here. You can compute the probability of that case happening plus the joint probability conditioned on that case, which in this case, a single mutation here guarantees xi is 1 and has no effect on xj. So the joint probability is actually just the probability of xj being 1. In the second case, we have no mutations in this half, but at least one mutation here. And we can compute the probability of that case and observe that in that case, both xi and xj are guaranteed to be mutated. So that probability is 1. And in the third case, there's no mutations here, so xi has to be 0, so the joint probability is 0. Now, these 3 cases are a partition of the event space, so applying the law of total probability and Bayes rule, we just multiply each pair together and add them up, and we get our lemma statement. Okay, and if you didn't follow this, don't worry, forget the last 2 minutes happened. Let's just move on. So from this joint probability, we can now easily compute the variance, because the variance is the sum of all these pairs minus the square of the expectation. And when I say easily compute, I mean it took us probably more time than I would admit, because it's sort of tedious algebra and it's very easy to make mistakes, but it is just algebra in the end. Now, once we have the variance and expectation, if this was a binomial, then life would be easy, because the way we would do a hypothesis test or confidence interval for a binomial would be just to approximate it with a normal distribution. But in our case, it's not clear that we can do that because we're not a binomial. However, it turns out because our dependency structure is so localized, we will be able to do it. And this comes back to a definition from 1948 of M-dependent variables. So that definition states that a sequence of random variables is said to be M-dependent if there exists a bounded M. Okay, so it will have M equals k minus 1, for example. So that if you put this block anywhere in your sequence, of kmers or variables here, then the xi's on the left, the set of xi's on the left, and the set of xj's on the right are independent of each other. So all the dependencies are more local, and that's exactly what's happening with nmut. That's exactly what our that lemma we just saw gave us. So nmut is then the sum of m-dependent variables with this value of m. Now, the nice thing about m-dependent variables is that their sum is also asymptotically normal, and moreover, if we use Stein's method, we can also get the rate of convergence to this normal. Therefore, we can now apply the same type of strategy that is used to get hypothesis tests and confidence intervals for the binomial. And so we state this in what I call the main technique theorem, which is the main technique we're going to use here, which is that if x is the sum of m-dependent Bernoulli random variables, then with limiting probability alpha, x lies in this interval centered around its expectation plus minus the z-score times the square root of variance of x. Let me explain some of those terms. So the z-score, if you haven't seen it, it's basically the interval on a normal distribution that would capture alpha % of the data. And this is something that's very easy to look up in a table, or there's in a programming language you can usually have a function to compute this. So this with the interval z alpha you have, and then the rest is the variance and the expectation, which you hopefully have computed. The limiting here refers to as L goes infinity, and this is often the case with these confidence intervals. The star here is to indicate that I'm hiding some detail that L has to be independent, and depending on how you apply it, for example, might have to be independent of K or of R1 in order for this to formally hold. But I'm not going to focus on that in the talk. So let's apply this then technique straight to nmut, and we've already computed the variance, which I'm not going to plug in here, but we know it, and we have the expectation, and so we immediately get a hypothesis test for nmut. Now, to compute a confidence interval, observe that this interval here is a function of R1, right? We have this RK, and this variance is a function of R1. And nmut is something you observe. So for a given R1, either nmut falls in this test range or it doesn't. And so what we are going to do, well, we could solve this equation for R1, and then we would get a confidence interval, but that's algebraically difficult, and we didn't pursue that. So instead, we just are able to numerically find the range of R1 for which nmut, the observed nmut, is in this test range. Okay, and in our paper, we have a proof of why this works. Now, let's go beyond nmut. If we, for example, observe some variable that's a monotone function of nmut, for example, Jacquard would be a monotone function of nmut, then there's a corollary. If a variable belongs to an interval, that's true if and only if the monotone mapping of that variable belongs to the monotone mapping of that interval. Okay, so we have this general statement, and we can apply it to the Jacquard to have a to have a hypothesis test for the Jacquard. Now, the Minhash Jakarta estimator is a little bit harder because now we have two layers of randomness. We have the mutation process for which we can apply our main technique, but we also have this sketching process which has randomness from a hash function. And here our main technique does not apply because the sketch uses global information. So we use a different approach, which unfortunately there's no time to discuss, and we get also a hypothesis test for J hat, which again, unfortunately, we don't have time to even define this exactly in the talk, but it's all in the paper. Let's look at another random variable in this model, an island and an ocean, or sorry, the number of islands and the number of oceans. So what this is if you look at this sequence of kmers, then you can partition them into islands and into oceans, which an island is a maximal interval of mutated kmers, and an ocean is a maximal interval of non-mutated kmers. So how do we get a hypothesis test for the number of islands? Well, we first write down this variable as a sum of m-dependent variables. In this case, for every position I, we can define whether it's a border or not. And it's a border if the kmer at that position is mutated and the one in the next position is not. Then the number of islands is just the sum of the number of borders, and now we can apply the same technique that we discussed. So we derive this joint probability of two borders being 1. We confirm that the status of being a border is independent if the I and j is far apart. We derive the expectation and the variance of n island, and then we apply our main technique theorem to get a hypothesis test. This is the summary of our theoretical results, and I already discussed almost all of these. The one part which I didn't discuss is the coverage by exact regions, which is a random variable defined by McClott et al. In 2016, which we also studied and derived an interval for. Some experimental results. So looking at nmut confidence intervals, what we did is we did a simulation where we started with a sequence with no duplicated kmers, and then varied k and r, and for every value of r and k, we did 10,000 replicates, and in each replicate, we took the observed nmut, we computed a confidence interval for r1 from it, and we checked, does the true r1 fall into that predicted interval? And we reported then the fraction of replicates where this is true. This is the definition way of checking, verifying the definition of confidence interval. And we see really good results for large L. As L gets smaller to 1,000, we still see very good results. As L gets to 100 now, we see this is where the L goes to infinity, starts to not hold for some values. We also did a similar experiment using not a sequence without duplicates, but the coli sequence, and we also see good results. We also tested the Minhash Jakarta estimator, and now I'm running out of time. So we basically replicated a table from the original paper, but instead of reporting the point estimate, we're reporting the validation of the confidence interval as a function of different sketch sizes and mutation rates. And we see, again, very good results, except for some extreme values of R1 and very small sketch sizes. Also, we did this with E. coli and got similar results. Finally, we looked at the application with read alignment. So one was Minimap 2, which filters out alignments if the R1 estimate is far from the sequencing error rate, and it has its own way of estimating R1. But instead, we used our model to do our R1 estimate, and here, even as a function of different R1s, we have a smaller error, the blue, than Minimap does in the red. In Java, which is a tool from McLeod et al., they have also a strategy for filtering out alignments, but instead of estimating R1, they measure the coverage by exact region. And this CBER, if it significantly deviates from the expectation, they discard the alignment. But they don't really describe what this significantly means. And in our case, we have a way to do this formally, to come up with a hypothesis test for CBER. Here you see the two lines above or below giving the 95% interval. And so we can discard reads which has a CBER score that's too low or too high. So to conclude, we took the simple mutation model, which has been, we didn't introduce it, it's been widely studied, but it's never been studied in depth as far as we know. And we looked at it in more depth, and we gave a technique for deriving hypothesis tests and confidence interval in this model. And this technique, what it does is exploits the fact that the kmer dependencies are local. We then applied this technique to some natural random variables. And as I think is the big remaining question, I think theoretically is, you saw that in some cases the approximations don't work well. This is because they're only true theoretically for large L. And so, for example, this is normal. For a binomial, we know that when np times 1 minus p is low, we don't expect the normal approximation to be very valid. So it'd be interesting to derive this similar type of formula for m-dependent random variables. And that's the references, and I'll stop here. Thank you.
Thank you very much. So we already have some questions. What happens if the assumption of uniqueness of kmers is relaxed? Does the analysis extend to weighted Jacquard?
I would have to think about how it would work for weighted Jacquard, but I do think that all the technique seems to rely heavily on this assumption of uniqueness. So yeah, I'm not sure how it would extend off the top of my head to the weighted Jacquard case.
Okay, thanks. Second questions. Could we think of updating this model to take into account random Bloom filter false positives and false negatives if we think of Lucas square filtration approach?
I think yes, Pierre. I think that just adds another. In a way, it should be like another chance that the kmers becomes mutated, basically if it becomes a false positive. So I suspect that this could be taken into account, but one would have to think more about it.
Okay, thank you very much.